In this video, we're going to take a look at a slightly different differential equation, and it might look very similar to ones you've seen previously, with one big difference. Let's say we've got y double prime plus y is equal to 0. And we're going to ignore all the initial conditions, and just try to find one solution to this. If you recall, we did something very similar previously, where it was y double prime minus y equals 0. And over there we found the solutions e to the x or e to the t, and e to the negative x or e to the negative t. Over here, and let's work with t rather than x, just because that's more standard for these sorts of questions. We're going to try to take another look at this and just think about it. We kind of touched upon this when we did y double prime minus y equals 0. And one possible solution to this is definitely sine of t. Sine of t. And with sine of t, you can have a whole host of other functions. You can have like 5 sine of t, negative 5 sine of t, negative 5i sine of t. All of those, because that's just a constant in front, and that doesn't matter. So we're just going to ignore that and just look at the core part of this that matters to us, which is sine of t. If you notice, cosine of t also works, and these two solutions work. But so far, we haven't seen anything like this. We actually went all the way and we found an entire process. We create the characteristic equation, we find R1, R2, and we didn't seem to see sine or cosine anywhere. So how could this be? Well, let's take a closer look at what we did before this. And let's also look at that assumption that we made. When we did AR squared, when we did AY double prime plus BY prime plus CY equals 0, we made this the characteristic equation AR squared plus BR plus C equals 0. And after this, we assume that the solutions to this R1 and R2 are distinct and real. Now, is that always the case? Of course not. And if you notice, the equation which we did above this did not have this case. The B was 0, A was 1, and the C was also 1. And if you work it out, if you create the characteristic equation and do it, you'll see that, of course, the solutions are not real. They're in fact imaginary. And when the solutions are imaginary, we can write them in this form. R1 will be lambda plus some mu I, and R2 will equal lambda minus mu I. And well, we can actually use this. We can use these solutions and put them in the exact same way we did before. And what you'll notice is that we get something like this: C1 e to the lambda plus mu I t plus C2 times e to the lambda minus mu I t. And well, this looks a lot more complicated than before. It's almost as if we can't do anything about it. And how does this relate to the sine and cosine that we saw, right? Well, we can break this up a little bit. So let's, just for the sake of space and simplicity, we're just going to examine this one, and we're going to even ignore the C1. We're just going to look at e. We're just going to look at e to the lambda plus mu I times t. This is of course e to the lambda t times e to the mu I t. And if you remember this now, well, this can actually be written in terms of sines and cosines. And this can be written as sine of, this is the same Euler's form, so it can be written as cosine of mu t plus I sine of mu t. And in fact, if you let mu t equal to pi over here, you get e to the I pi. And if you let mu t equal to pi, as I said, this will be negative 1, this will be 0, so it will just be negative 1. So it will give you that famous identity, e to the I pi equals negative 1, or e to the I pi plus 1 equals 0. So that's how we convert it. Now if you look here, this is the right hand side, this factor over here, we've still got this, so we just stick that in front. And this is now what we have. So we did find it actually, and it makes sense. We've got it in terms of e to the some power t, and then we've got cosines and sines. This is that pesky little I though, and we'll see how we can deal with that. We can follow a very, very similar process for this. So we've got C1 and then this, and then we'd have C2 e to the lambda t. You can work this out on your own, I encourage you to do that. Cosine of mu t, and this will be minus I sine of mu t. And we're adding these up, so let's go ahead and do that. What are we going to get? Well, we're going to get C1 plus C2 e to the lambda t cosine of mu t plus, I'm going to put a bracket there, you have I times c1 minus c2 e to the lambda t sine of mu t. What are c1 and c2? They're both constants. What is I? It is a constant as well. So we can now write this as some mu c, let's call it c3 e to the lambda t cosine of mu t. And over here, this is again just a constant, so it's c4, a new constant, e to the lambda t sine of mu t. And with that, we're done. This now matches the form earlier where we saw c1 y1 plus c2 y2. Right, so over here y1 is going to be, of course, e to the lambda t cosine of mu t. Y2 is going to be e to the lambda t sine of mu t. And this actually gives us something very interesting to look at. We can now we can find the characteristic equation. We can find this and just plug it in directly here, and it will make perfect sense to us because we can just find the lambda, we can find the mu, plug it in here. It's a quick and easy formula to use. And this is now open our arsenal. It's widened it quite a bit. Now we can have distinct real roots, we can have distinct complex roots. All that's left to examine is what you do when you've got non-distinct roots and you've got repeated roots. And we're going to take a look at that in the next video, in a few videos actually, because I want to do some example questions of this and see how we can actually solve questions given lambda, mu, and best practices regarding that. So I'll see you soon.